Ever stop to think about what's really going on inside your phone? I mean, you tap the screen, something happens. Or, how does an automatic door just know you're there? It kind of feels like magic, right? But it's not. It's actually this incredible microscopic performance, this high-speed dance that's happening billions of times a second. So today, we're going to pull back that curtain and take a look at this unseen symphony. There's this quote from a research paper. Yeah, a research paper on semiconductor design, but it just hits the nail on the head. It says that just like a conductor guides an orchestra, time enclosure orchestrates the flow of signals inside a chip. And that's really the key, isn't it? It's not just about having all the right parts. It's about perfect, coordinated timing. It's like having this tiny, invisible orchestra playing inside every single piece of tech you own. So, how does this invisible little orchestra actually play? Inside your phone or even that automatic door? Well, that's exactly what we're going to break down. We're going to follow a single signal on its amazing journey, starting from the real world, going deep into the digital brain of a device, and then coming right back out again. So let's start at the beginning. All right, so every single interaction has to start somewhere, right? And for a device, that's with sensing. Before it can think or react or do anything at all, it has to sense the world around it. This is where the first section of our orchestra comes into play. And those players? They're called sensors. They are, quite literally, the eyes and ears of any smart system. Their one and only job is to take something physical from the real world, like, say, the heat from your hand, or you walking towards a door, or even just the light in a room, and turn it into an electrical signal. Think of them as the translators, the bridge from our world into the digital one. Now, to really get the whole picture, you have to understand that sensors have an opposite, a counterpart. They're called actuators. It's actually pretty simple. Sensors take in information from the physical world and turn it into an electrical signal. Actuators, and we'll talk more about them later, do the exact opposite. They take an electrical signal and turn it back into a physical action. So one listens and the other speaks. Two sides of the same coin. Okay, so our sensor has done its job. It's created a signal. That signal now travels to the processor, the digital brain. And inside this brain, things get intense. We're talking about billions of components and this crazy, high-stakes race against the clock. And this whole engineering puzzle, this challenge of making sure every single signal arrives exactly when it's supposed to, that has a name. It's called timing closure. Probably the easiest way to picture what's happening is to think of it like a relay race, a super, super high-speed one. In this race, you've got the processor and the memory as two runners. And the data? Well, the data is the baton they're passing back and forth. But here's the crazy part. This isn't some school track meet. This handoff is happening billions of times, every single second. So let's break that handoff down. Step one, the CPU, the processor, gets the data baton all ready to go. Step two, it places that baton onto what's called the memory bus. Think of that as the racetrack itself. And then step three, the memory controller has to snatch that baton, but it has to do it in this incredibly precise, tiny window of time that's synchronized by a clock signal. That clock is like the starting pistol for every single handoff. And for this whole thing to work, there are two rules. Two critical, non-negotiable rules. First, there's setup time. This just means the data baton has to be held steady before the clock signal arrives. It has to be ready to be grabbed. The second rule is hold time. This means the baton has to stay steady for just a moment after the clock signal so it doesn't get misread. You break either of these rules, the baton gets dropped. It's all about that perfect split nanosecond synchronization. So what happens when the baton gets dropped? Well, the consequences are things we've all felt. You ever have a phone that just feels sluggish? Or your computer just completely freezes up and you have to reboot? Yep, that's a timing failure, a dropped baton. It can cause data to get corrupted, performance to tank, your battery to drain faster, and in the worst cases, it can actually cause permanent damage to the chip itself. This is exactly why getting that timing right is so, so important. But there's another side to this high-speed race. Just like a sprinter after a 100-meter dash, the processor gets hot. All of that constant activity, all that switching, it burns a ton of power and generates a massive amount of waste heat. And when I say massive, the scale of this problem is, well, it's pretty staggering.
Just look at this graph. It's actually kind of mind-blowing. What you're seeing is power density, how much power is crammed into a tiny space on computer chips over the years. And check this out. Processors have already surpassed the power density of a kitchen hot plate, and the trend is heading towards the same density as a nuclear reactor. Now think about that. All of that heat, and it has to be managed inside something you can hold in your hand.
So where is all this power and heat coming from? Well, it breaks down into three main culprits. The biggest one is switching power. That's just the energy it takes to flip billions of tiny switches on and off over and over again. Then you've got short circuit power, which is basically tiny, brief sparks that happen during a switch. And the third one, which is getting to be a bigger and bigger problem, is leakage power. The parts inside are so impossibly small now that electrons can literally just tunnel right through the material. It's like a slow, constant leak in a tire.
And all of this leads to this fundamental problem, this huge trade-off for the engineers. See, the easiest way to save power and cut down on heat is to lower the voltage. But there's a catch. As you can see here, when you lower the voltage, the delay, how long it takes for things to happen, goes way, way up. So you're stuck in this constant battle. Do you want a blazing fast, hot, power-hungry chip, or do you want a cool, efficient, but slower one? Finding that perfect sweet spot, that's the real art of designing these things.
Okay, so let's recap. Our digital brain has gotten the signal. It's run its super fast, perfectly timed calculations. It's made a decision, all while trying not to overheat. So, now what? Now it's time to actually do something in the real world. It's time to bring in the hands and legs of the system. And that's the job of the actuator. Remember, we talked about this earlier. It's the total opposite of a sensor. It takes that final electrical command from the processor and turns it back into a real-world physical action. This is the part that actually makes a motor spin, a light turn on, or your phone vibrate. And actuators come in all shapes and sizes. In the gadgets we use every day, they're usually electric, like that tiny motor that makes your phone buzz. But in bigger machines, you'll find actuators that use liquid pressure, that's hydraulic, or compressed air, which is pneumatic. Some even use heat to trigger an action. Pretty cool. All right, we've seen all the pieces. Let's put it all together now. Let's follow that entire journey one more time. This whole unseen symphony from start to finish. So it all starts with something simple. You're walking towards an automatic door. A motion sensor, the eyes of our orchestra, sees you coming. It takes that movement and turns it into a tiny electrical signal.
Instantly, that signal zips over to the processor, the digital brain of the door. Inside, that high-speed relay race kicks off. In a fraction of a second, billions of calculations happen, all perfectly timed, and the processor makes a decision. Yep, someone's here, open the door. And then, the final step. The processor sends a new command out, this time to an actuator, which is probably an electric motor. The actuator gets that signal and turns that digital yes back into a physical action. The motor turns, the door opens, and you walk through. And just like that, the symphony has played its tune. Sensing, processing, acting, that whole loop. It happens almost instantly for something as simple as a door, and it happens billions of times a second inside the phone that's sitting in your pocket right now. It's this absolutely incredible, invisible symphony of perfectly timed complexity, which really just leaves you with one thought, doesn't it? What's it going to learn to play next?